Good afternoon. Today we're going to talk about support vector machines, and I'm going to start with the idea of creating a classifier that maximizes the margin, so the distance to the closest point. And then we're going to see how this develops in a support vector machine. This is going to take a bit of math, but don't be afraid. The idea is that you understand the final result. You don't need to memorize the demonstrations and so on. So we'll start with this notion of maximum margin, the support vectors, and then we'll see how a support vector machine works. Then we're going to, after the break, we're going to continue with support vector machines, because then I'm going to show you why this is important and what the usefulness of this kind of classifier. So let's start with the notion of the maximum margin classifier. Let's take, for example, this prediction of cancer from the gene activity profile, this data sample, and we want to separate the two classes with a line that goes somewhere around here. And we saw our first approach where we tried to minimize the distance to the points. We saw that this was not very good because the line is affected by points that are far away, and this way we were able to understand well the difference between regression and classification. When you're doing regression, you're trying to fit something as close as possible to your data, but when you're classifying, you're trying to split the data sets into subsets. This means that the frontier should be far away from the points and not close to the point. So we solved this with logistic regression, where we're trying to do a regression to a function that gives us the probabilities of belonging to each class, and then we use those probabilities to do the classification. And this worked because we have this logistic function that has this step in this way, so it gives us the probability of belonging to one class in this manner. This means that those that are here have a high probability of belonging to class 1. Those that are on this side have a low probability of belonging to class 1. So this allows us to create a line between the two classes. One problem with this is that since we can arbitrarily increase the size of the vector that will determine this plane where we cut our set, so the hyperplane that separates our data is defined by a vector that is perpendicular to the plane, but the size of this vector can be anything we want. And in this case, if we have a very large vector here, this means that this function changes very rapidly. This degree is very steep, and so we can put the step here wherever we want, arbitrarily close to any point. And we thought that this was a bad idea because of overfitting. If we allow the frontier to go very close to one point, or to be deceived by some spurious data, by some outliers, we can have problems with overfitting. So the way we solved this was to use regularization in logistic regression and try to shrink the size of this vector. As we reduce the size of the vector, we make this step smoother, so less inclination here, and we force the frontier away from the nearest point. So basically, with regularization, we are penalizing the size of this vector, and we force the discriminant to be here in the middle, because if it's too close to one side or too close to the other, since this change is no longer as steep, it will start to increase the error on one side or the other. So this was a first approach to the idea of trying to maximize the margin, trying to keep the discriminant away from the point in order to minimize the mistakes we are going to make outside our training set, or minimize overfitting. So we did this by adding this penalty. So we have our cost function. The original logistic cost function would be that one we're trying to minimize. But to this cost function here, those products of the sums of those logarithms multiplied by the class, we also add an additional term. So this term, which is the size of the vector, the coefficients of that vector, squared and all summed up. So this increases the margin indirectly by changing the function we're trying to optimize. So basically we can see this as a bit of cheating. We are no longer aiming at that cost function for trying to minimize the error between the predicted probability and the target probability, but we are changing that cost function, and that's one of the ways of doing regularization. We change the way the model is trained in order to try to keep the frontier away from the closest point. So from here we can better understand this idea. So we have a margin classifier, which is a kind of a classifier that allows us to compute the distance between one point and the discriminant. For example, we can do that with logistic regression because we know where the discriminant is. We cannot do that easily with k-nearest neighbors. We don't have an explicit description of where the discriminant is. We could compute it indirectly, but we don't have it as available. A maximum margin classifier is one that tries to maximize the margin. So the idea here is that not only do we want to separate our data into the two classes, but also we want to put the discriminant as far away as possible from the closest point. So we are trying to maximize the distance to the nearest points we need to separate. If we zoom in this case, this data set, if we look at this region here, we can see that there are points over here and over here that don't matter for placing the discriminant. Because they are farther away, it doesn't matter where they are, and they don't force us to change where we put the discriminant. But these 3 points here, which are the ones closest together to the frontier, to the discriminant, are the ones that are determining where we must put the line. So these are the support vectors, the ones that determine where the discriminant will be. And the idea of this maximizing the margin would be to maximize the distance to the closest point, so the distance to the support vector. And this is basically a very simple idea. All we need to do is find which points are closest, measure the distance, and try to maximize the distance. We could easily implement that. So we can build this expression that will give us a signed distance to the plane. Signed because when we compute the inner product between the vector that determines the hyperplane and each point, it will be positive on one side and negative on the other. So as we go on the back side of the plane, the product will be negative. And if we divide by the size of this vector, this will normalize those values, so they will become independent of the size of the vector, and this will give us the distance to the plane, but with a sign. On one side the distance is positive, on the other side the distance is negative. So now we can assume that we have two classes, +1 and -1, and we can multiply the class by this value. So if the signed distance has the same sign as the class, it will be positive. This means that we want the -1 class on the side of the negative values and the +1 class on the side of the positive values. So this will be the distance to the points that are correctly classified. The closest point will be the minimum of this distance. And since we want to maximize the margin, we can compute the minimum distance to all the points, and then we try to find the values for our discriminants, for the vectors, that maximize this value. So we want to maximize the minimum distance to the point. And this is easy to implement. All we need to do is we define this closest distance function, so we receive all the values for our hypothesis, all the parameters for the vector, the values, the positions of our examples, and the classes for all our examples. And now we create here a new vector that is a column, so we can do the dot product here. We do this multiplication, the vector multiplied by all the examples, and adding the other W0 there. And then we divide this by the size of the vector and compute the distance, so the square root of those Yes. Well, this X here is all the data, the training data. So this is a matrix with all our training sets. So basically this is just the computation of this part here, and then we compute the minimum value for all these distances and return the minimum value. Since we want to maximize, to find the values that maximize this function, but we have a minimized function in our toolkit, we just change the sign there, but the idea is the same. So we're trying to find the maximum, we are trying to maximize the smallest distance to the point, and this will be maximizing the margin. So we can implement this in less than 10 lines of code, then we run and it doesn't work. So we run several times and it's always the wrong answer. So this is, in theory, it should work, it should be easy to do. We just maximize the distance to the closest point. But when we try to solve this numerically, we have this problem. The algorithm for minimization cannot find the solution. And the reason for this is that as we are changing the position of the discriminant, the closest points can change. So at some point there are 2 or 3 points that are closest, but then there are other points that are closest, and these keep changing. As we change the position of the discriminant, the distance to any particular point changes smoothly. But if we plot this function here, the distance to the closest point, we have something like this, with these jagged edges in all those combinations of values, where we go from one set of points being closest to another set of points being closest. So you can imagine that the distance to any point is a smooth quadratic function, but as we change from one point to the other, we abruptly change to another function. And this means that there are discontinuous derivatives here. So the derivative changes abruptly, is not continuous, and worse than that, the derivative is discontinuous precisely at the point that we want, at the maximum here, because the maximum is where we are exactly stuck between those specific 3 points. As we change, other points will appear. So this is why we cannot solve this minimization problem, because we cannot rely on the derivatives, and we need the derivatives for those gradient descent algorithms. So the idea of building a maximum margin classifier is very simple and intuitive. It's easy to implement, but then it doesn't work. And this is one important aspect of machine learning. You not only need to make things in theory to work, but they must be computable. So you must have some way for the computer to find the solution. So now we go to support vector machine. The idea is, how can we solve this problem? How can we transform this problem so that it becomes something the computer can solve, and we still retain this basic idea of maximizing the margin? So we continue with this idea, find the maximum margin. We cannot compute it because of the discontinuities in the derivatives if we do it just like that. So now we're going to go through some equations, but don't be afraid, you don't need to memorize all the steps. The basic idea is that when we reach the final form of the support vector machine, you have an understanding of where the different parts come from. So let's start by noticing that this normalized distance, when we measured that distance to the discriminant, we divide it by the size of the vector that we are using, and so this is independent of the size of the vector. We have always the same distance measure, regardless of whether we use a large vector to define the hyperplane or a smaller vector. It only depends on where the hyperplane is. So we can, by arbitrarily changing the size of this vector, we can assume that we will always be able to do this. For any point that we have, the margin, or that sign distance there, without the normalization, will be at least 1. So notice that we are considering here the distance to the sign distance to the plane, but then multiplied by the class. So points of class 1 will be on the positive side, points of class -1 on the negative side. So this we assume we can do simply by changing the size of the vector. If the points are too close together, we can use a vector with a larger size, and we increase this value, and so that it's greater than 1 for all the points. So now we can, if we stick this constraint, if we assume enforce this constraint, then our problem of maximizing the distance to the closest point becomes the same as minimizing the size of the vector. The reason for this is that if we shrink the size of the vector, then this value will be smaller, and we will have to start moving the discriminant away from the closest point in order to be able to keep shrinking the size of the vector. At some point, we cannot shrink anymore the size of the vector, but at that point, the discriminant is as far away as we can put it from all the points correctly classified. So basically, this problem becomes this problem, finding the minimum value for the for the size of the vector. Which parameters will give us those values? So now we can solve this problem. This is a much simpler one. It doesn't have that problem with the discontinuities of the derivative, because we are simply reducing the square of or the sum of the squares of the values of the parameters we use to define the vector. So there are no discontinuities here. Unfortunately, we have this additional problem. We don't have just a minimization problem now. We have a constrained minimization problem, because we need to minimize this, but at the same time never allow the margin to be smaller than 1. So this is, we transformed one problem into another one. We solved the problem with the discontinuous derivatives, but we added this complication where we have the constraint. So how do we solve a constraint optimization problem? We use this methods called Lagrange multipliers. I'm going to explain this very briefly, so I'm not going to derive everything, but it's important for you to understand at least the general idea of what the Lagrange multipliers are, because that's what we're going to compute in the support vector machine at the end. So let's suppose, with a simple example, we have this function 1 minus x squared minus y squared, and we want to find the maximum of this function. So this would be a simple maximization, optimization problem. But we want to do that subject to that constraint, x minus epsilon minus 1 equals 0. So x minus epsilon minus 1 equals 0 is a line that goes in this way. So it cuts our original function over here, and we want to find the maximum of the function along this line. So this is an example of a simple constraint optimization problem. We want to find the maximum of this function subject to this constraint. We cannot step outside that line. We can understand intuitively that along this line, when we reach the maximum possible value for the original function, this line must be parallel to a contour line of the original function. The contour line is a line that has always the same value, the same result. It must be parallel to that, because if it wasn't, then we could be able to increase a little more, and we wouldn't be at the maximum. So we are only at the maximum value when we are parallel to a contour line of the function. So this gives us this idea. This function here, x minus y minus 1, has a contour line at x minus y minus 1 equals to 0. Because if we compute the function equal to something, that is by definition a contour line of the function. So the contour line of this function, x minus y minus 1, must be parallel to a contour line of this function we're trying to maximize when we reach the maximum value. Because the constraint is itself a contour line too, and they must be parallel. So basically the idea is that when we find the maximum of our function subject to one of these constraints, we find a point where the contour line defined by the constraint of the function we are using to constrain is parallel to a contour line of the function we're trying to maximize. If the contour lines are parallel, the gradients of the function must be parallel too, because the gradients are always perpendicular to the contour line. If we have this line where the value is constant, the gradient must always be perpendicular to this value, because otherwise the value would change along the line. And if it's a contour line, the value cannot change. So basically, this is the idea. When we find the maximum of one function respecting a constraint defined by another function, the derivatives of the two functions at that point must be parallel. They can be in opposite directions or someone if we are imposing just an equality constraint here, but they must be parallel to one another. And this is the condition that we can impose for the maximum. The gradient of the function we're trying to maximize must be some value multiplied by the gradient of the function we are using as constraint. If the constraint is an equality constraint, it doesn't matter what the sign is here, because we can use any sign and then change the value. But anyway, by convention, we use a minus sign here, so that when we write the Lagrangian, this is a new function, we get this sum over here. So basically, the Lagrangian is the sum of the original function that we're trying to maximize and the function that we are using as constraint multiplied by this Lagrangian multiplier. And now we solve the problem by finding a critical point in the Lagrangian, so one in which all the derivatives of the Lagrangian are 0. So this is the technique for going from a constrained optimization problem into a simple optimization problem, or in this case, finding the critical point of a function by incorporating the constraint as an additional term on the function we are working with. So for our example, we write the Lagrangian for our function with the constraint, and now we solve for when all the derivatives are 0. This gives us a value of 0.5 for x minus 0.5 for y, which is this value here corresponding to the optimum there. So this is the idea for solving the constraint optimization problem. We saw here with this example, to simplify, we have a constraint of the type some function equal to 0. If the constraint is some function less or equal to 0, for example, we have to take care with the sign of the Lagrangian multiplier, but we're not going to go into much detail there. Just suffice it to say that we can use the same thing for our problem. So we want to find the minimum size of the vector, or the minimum of the sum of all the squared coefficients for our vector, and we want to find it subject to this constraint. So for all the points, each point will give us one constraint, so we have a set of constraints. For all the different points, if we multiply its class label by the inner product of the point and the vector that defines the plane, it must give a value equal or greater to 1. We can rewrite this to have a 0 on that side, so rewriting the constraint, it will be like this, minus the class label multiplied by the inner product of the vectors and so on. So now we can write the Lagrangian. We have one constraint for each point that we have in our training set. Remember that this must be true for all the points. So we'll have one Lagrangian multiplier for each point we have on the data set. But the expression is always the same, so we can write this as a sum. It will be our original function, then the contribution of one constraint, another constraint, and so on, but we group it all together in this sum here. Since there is a negative sign there, we can put a negative sign here, and we write the Lagrangian function for solving this problem. At the critical points of this Lagrangian, we know that all the derivatives are equal to 0, and we can solve the equation there, and we find at the critical point what is the value of the direction, the vector defining our hyperplane as a function of the Lagrangian multipliers, the classes and the positions of the points, and the same thing for the extra value that tells us where the plane is placed, it's W0. And if we replace here, I'm not going to do all the steps, but basically replacing this here, we find the dual representation of this problem. And the idea of a dual representation in mathematics is that you have a different problem, but that gives you the same result, basically. So this minimization, this can be solved by maximizing this expression with respect to the Lagrangian multiplier. And this is the final shape, what we're going to solve for the support vector machine. We are maximizing the sum of the Lagrangian multipliers, each one corresponding to each one of the points in our training set, minus this product. So this is the Lagrangian multiplier multiplied by this, but we can write that vector as a function of this sum for all the points. So actually we get here two sums, and basically we have a matrix with all the inner products of all our data points of our training set, all the products of their corresponding classes, and the products of their corresponding Lagrangian multipliers. So this is where we got to. We have to solve this new problem where we have as many variables as the number of training points we have, because each training point provides one constraint, and so it has one Lagrangian multiplier associated with it. And the expression is the sum of the Lagrangian multipliers, so we are trying to maximize the Lagrangian multipliers, but we are subtracting this term here, which includes the inner product of all the pairs of training points that we have, their corresponding classes, and their Lagrangian multiplier. We also have these constraints, so these come from the imposition that we are trying to find the critical point, so the derivative is 0. We know that the sum of all the Lagrangian multipliers, which are all at least 0 or more, so they're positive, multiplied by the corresponding classes. We have some points with class 1, some points with class -1. The sum of these must be 0. And furthermore, since the constraint is an inequality constraint, the Lagrangian multipliers must be all equal to or greater than 0. So let's see intuitively what this means. We are trying to maximize the Lagrangian multipliers, but we penalize this function whenever, according to this expression here. And what this tells us is we are multiplying, we are finding the inner product between two vectors. So if the vectors are pointing towards the same direction, their inner product will be larger. If they are further apart or in different directions, we have a smaller value here. And we are also multiplying the class label. So for all points that are surrounded by neighbors of the same class, this becomes a large number because it has all the contributions of their neighbors, and they are all positive because they both have the same class, so whether the class is -1 or +1, it becomes a positive value. And since this is subtracting from what we're trying, from the expression we're trying to maximize, this means that all the points that are close to neighbors of the same class will tend to have Lagrangian multipliers to 0. So that's the best way of maximizing this value. We minimize the penalty we are imposing here. When we have some points that are close to neighbors of the other class, then the converse happens. We have a negative term here because the classes are different with points that are close by, and so it pays to increase the size of these Lagrange multipliers because now this will be negative, and since we are subtracting a negative value, we can increase the value of the function. So points that are close to their neighbors of the same class will have a 0 value for the Lagrange multiplier. Points that are close to neighbors of the other class will increase the value of their Lagrange multiplier, but we have this constraint. The total product of Lagrange multipliers with the class labels must be 0. So if we increase with a point from one class, we must find a point on the other class to increase to, and at some value, this will stabilize and we have the maximum of the function. So this is what the intuition for what we have here. But notice that the variables here are one Lagrange multiplier for each data point. We are no longer concerned with the W, with the actual expression for the discriminant hyperplane. And this will be very important for after the break when I explain how we can use this. So this is just a simple example that you will not have to do, but just because we are going to use support vector classifiers from the scikit-learn library. So you just create the object, give in the parameters, and it will give you the result. But in order to understand what is going on inside, I will just show one possible implementation, not optimized, but that you could do with the tools that we have. So we are trying to maximize this. We can call this part here. So this is the inner product of all pairs of data points that we have in the training set and their corresponding classes. We can just pre-compute this because this is fixed. It's always the same matrix. So we call this the age matrix, which is all these products here. This is the function to compute that. We create a matrix which has the same, in rows and columns, the same number of values as the data set has points. So if we have 100 points, this is a matrix of 100 by 100, and we compute for each position on the matrix the dot product of these vectors. So remember that all our examples, our data points, are vectors of coordinates. They can be in 3 dimensions, 4 dimensions, whatever, but we compute the inner product of the vectors, which is always a scalar value, and then we multiply by the class labels, and we compute this matrix. Now we need the loss function. So the loss function is this expression here. So 0.5 times we can do this as a matrix multiplication. So we have the alphas, and then this matrix multiplied by the other alphas, and we can compute for everything in one go. And this is positive instead of negative because we have a minimization function. So when we call minimize, since we want the maximum, we have to change the sign. So it's always the same trick. We always use a minimize function, but we change the sign. It's the inner product with itself. So basically, it depends on the size of the vector. So in the diagonal, they are multiplied by the same vector. We also need the derivatives, but basically this is the derivative of the function with respect to the alphas. But this is because of the minimization algorithm. I'm not going into detail there. But usually, when you have simple minimization, it works relatively well by computing the derivatives numerically. If you have more complex problems, you should provide a function that gives the derivative, so pre-compute it analytically in order to facilitate the algorithm. So this is basically the derivative of this function we're trying to maximize. And now we load the data. These are all our values, class 1, class minus 1. We compute this matrix with all the inner products. This is how we define the function, the constraints. So basically, we also need to provide the function for the constraint. The constraint is this one. The alphas multiplied by epsilon equals to 0, and also the derivative of that function to facilitate the computation. But we don't need to go into much detail there. Basically, this is a dictionary that specifies this constraint here. And now this is basically a sequential quadratic programming problem. So we use that sequential least squares programming method, and we start with a random value for our initial guess, and so this has the same number of values as the Lagrangian multiplier, which is the same number of values as we have in our training set. And now we minimize this function, which is the symmetrical of that. So actually we are maximizing that function there. And now we can find from the solution. The solution will give us a vector with all the values of the Lagrangian multiplier. So here we can print the values for all the Lagrangian multipliers that are greater than 0.001. The reason for this is that we should have lots of them at 0, but since they are rounding errors and there's a limited precision on floating point numbers, we don't actually get exactly 0. But you can see that most of them are false except 3. 1 here and then 2 here. And if we plot them, they are these 3. So these are the 3 support vectors. These are the 3 examples for which the Lagrangian multiplier is not 0. So the results, when we train the support vector machine in this way, we found the 3 points that are critical for separating these classes. All the other ones don't really matter. It doesn't matter where they are. These 3 ones are the ones that we care about. And now we can compute the values for the discriminant. We know that the values for our discriminant can be provided by this sum. So the discriminant times the class times each point added for all the points. Remember that these examples are vectors. If we sum all these vectors, we get a vector at the end, which is the vector that defines our hyperplane. Also note that we don't need to do this for all the points, because for most of them the Lagrangian multiplier, the alpha, is 0. So actually we only need to look at the support vectors in order to compute this value. So basically this is the computation here. We can also compute the W0, so this is the constant that determines where the plane is at, because for the support vectors we know that this value must be 1. So the support vectors are those that are closest to the discriminant. We impose this condition that this must be at least 1 for all the points. For the other points, we don't know how much this expression will be, because they can be arbitrarily far away from the discriminant. But for the support vectors, it must be exactly 1, because they are as close as possible to the discriminant. So basically, we can do this. We can compute where the line is at, and this is the result. So we managed to solve that problem of maximizing the minimum distance, which we could not do directly because the derivatives were discontinuous, but we changed the problem. Now we compute the Lagrangian multiplier for all the vectors, those alpha values, and we find in that way which are the vectors that are important to determine where to put the discriminant. Okay, so to sum up this first part, we saw this idea of maximizing the margin. If we don't maximize the margin, we can put the discriminant in lots of different places. This can result in overfitting, because it can be too close to where it shouldn't be. If we maximize the margin, we force it to be as far as possible from the closest point, and that in general minimizes overfitting, because we are less susceptible to small variations, to noise in our data. So this could not be solved directly because of that problem with the derivatives, but we changed it into a constraint optimization problem, which led to that method with Lagrangian multipliers. And now we end up, instead of trying to compute directly the position of the discriminant, we are computing the Lagrangian multipliers for all the points in the training set. So this is the problem we are now trying to solve. When we do that, we find out which of the points are important to place the discriminant, and those are the support vectors. And that is why this is called the support vector machine. We are going to look for the support vectors to tell us where to put the discriminant. So we have in Alpine and Marsland, we have some descriptions of this. And we're going to take a short break before I continue with the next part. Because at this point, it's not very clear why we should do this. We have a linear classifier. It seems to work more or less the same as a logistic regression. So there doesn't seem to be much point to doing this. But we're going to see that this particular formulation with the inner product sphere is very powerful when we do some modifications.